Okay, so welcome everyone to our webinar on digital twins. Thank you for joining. I especially would like to thank all speakers that are joining today to hear various perspectives from industry and also research. I will quickly go through the agenda so everyone knows what you can expect in the next 2 hours, and then I will hand over to the speakers. So first, we hear an introduction to digital twins from Els Nagels from InsPyro and from Francisco Romero from IDENER. Then it's all about the EU project Dust2Value. Manuel Leuchtenmüller from the University of Leoben will introduce it. And afterwards, the digital twin of Dust2Value will be explained by Els. Then we have the EU project BioFibreLoop joining as well. Thomas Fischer from the German Institutes of Textile and Fiber Research will introduce the project. And afterwards, Francisco is going to explain the digital twin of it. The last project that is going to be explained is the EU project FlashPhos. Christian Schmidberger from the University of Stuttgart is doing this. And then Els is taking over again to introduce the digital twin of FlashPhos. And then at the end, we have the use cases of the FlashPhos digital twins, which will be presented by Lukas Pohl from the University of Stuttgart and from Stefan Papkalla from the German Cement Works Association. Then at the end, as already mentioned, we have an open discussion and questions from the audience. So feel free to please note your questions during the webinar, and then you can ask them at the end. So I hand over to Els and Francisco now.
Yeah, thank you. I will start. Let me share my screen. Okay, welcome everybody. I'm Francisco from IDENER, and we'll be starting with the presentation of what is a digital twin in this webinar. But first, let me explain you a little bit what IDENER is and what we do. We are a research organization founded in Seville. Our headquarters are there. And we are a group of engineers, scientists in general, PhDs, and so on, with large experience in European projects. And what we do is basically everything related mainly to digitalization, computational modeling, classification and prediction, control of complex system, and mathematical optimization. All of this is embedded in the digital twin. So that's one of the things we do in IDENER, and we apply this in several sectors: energy, chemistry, materials, and so on. So let me first start with explaining what a digital twin is, what is the concept. The father of digital twins, Michael Greaves, and my colleague John Vickers define it as a digital informational construct of a physical system that it is an entity on its own, and it's linked to this physical system throughout its entire life cycle. So digital twins have four key elements, main four key elements, which are first, the physical entity is the real system or the process that you are representing. It can be a machine, infrastructures, a process. Next, a virtual representation, which is a digital model that captures its behavior. And all of this connected with a layer of continuous data exchange between the physical and the virtual system, which is the third key element. And finally, the lifecycle integration, because the digital twin will evolve alongside how the real system evolves. Okay. Next, the core capabilities of a digital twin, what a digital twin must and can do, is four main core capabilities. First is monitoring. They allow the real-time observation of the physical system. They allow to simulate it do virtual experimentation of it. Next, do an optimization of the key parameters that rules the different processes. mostly done by data-driven or other algorithms. And finally, allow the decision support and support these strategic decisions that can be done on the real physical space. So what are the advantages of a digital twin? First, they reduce the physical trial and error with it associated costs. They reduce the prototyping and so on. With this, they accelerate the innovation cycles because you can virtually test and iterate rapidly without needing to go to so much to the laboratory. So you can design modification and evaluate them quickly in this virtual environment. Next, you can enable with these data-driven decisions, which are informed and can provide real-time results of the trials you are trying to do to your process. And so they allow also for the optimization of production parameters, because this can allow to have a more efficiency, reliable and productive systems. They can allow also to integrate the sustainability from early stages, because you can optimize the use of the materials, improve the operational strategies so they can be more sustainable at the end. And finally, you can improve the traceability and the product understanding of the general process. Okay, so they can be more easy to show and to comprehend what is going on the full physical real process. But digital twins are also challenging to implement sometimes. They depend on several things. First, they rely heavily on data. So if the data is not available, is incomplete, is noisy, or difficult to measure, the digital twin will not work as properly as possible. Then the models, the physical and mathematical models you are implementing need to be good, needs to have a good understanding of it, because if not, you cannot really implement it correctly and also validate it with the real process. Sometimes you can model a certain unit, but extrapolate it to the whole process can be also complex, and it also will need interdisciplinary expertise collaboration. You need experts from the more scientific laboratory part, and also from IT and data scientist experts to collaborate. Also, sometimes the data can be scattered through different databases, because the data maybe already exists, but integrate all of this in a homogeneous database which you can use in the digital twin can be also challenging. And finally, start with an overly ambitious digital twin, which from the start represents the whole process, can be also difficult. So you usually should be developing digital twin with modularity in mind, but first starting with the most critical modules or units, and later on start adding them into the digital twin. So that's everything from my side. I will leave the floor now to Els to continue with the explanation. Thank you.
Yes, thank you very much, Francisco. And also a very warm welcome from my side. I'd like to, well, my name is Els. I'm CEO at InsPyro. And here at InsPyro, we make process models for industry as a service. And I would like to add a bit of a philosophical thought after the theoretical approach from Francisco, and this with the aim to inspire you to think about the goal and usefulness of a digital twin if you plan to make your own digital twins. As Francisco already told, data is a very important aspect of digital twin. So you have actually two backbones. One side is the data, the other side is the model behind it. When you look at the data, there is a bit of a ranking in how you can look at data. So the first lowest level of data is just the numbers, and they have some value if you can trust the numbers. So that is maybe the base level when you look at data. Then when you can find a way to transform these numbers into information, you actually take a step up. So just as a very simple example, you can have the number 1450. That is just a number. If you add the unit, so 1450 degrees centigrade, it becomes information. So your data gets more value. Then you can take another step and look at this information to become analysis. So for example, if you track the temperature over a longer time, you have a data series and you can actually analyze the data and gain insight. So that is a bit what we see as the third step into the data value chain. And then the final step is that when your analysis of your data can also help you to make fact-based decisions. And when you reason about digital twin, that is where your goal should be. Your digital twin should be able to support you to make fact-based decisions. So that is where the highest value creation is achieved. In the world of data handling, the digital concept of digital twin is a bit of a knowledge-centered approach. I'd like to make a little sketch to explain that a bit better. So we can look at two different axes. So on the horizontal axis, you have the data you have available. On the vertical axis, I plot the availability of physical knowledge. So what do I mean with that? So on the horizontal axis, let me make here a pointer. So here on the left side is when you have a situation where data is maybe available, but maybe not in digital format, so limited data availability. Then there is a middle route where data is digitally available, but maybe in different sources, so not connected data. And then you have situations where there is an extensive database where all data is collected in an easy accessible database. So in other words, if you need something, with one click, you can get the numbers and information from your database. And on the vertical axis, I'd like to plot the physical knowledge. So lower on the axis is there is very little physical knowledge. Higher up the axis is there is more knowledge. And then if we fill in this graph, you have a bit section. So I borrowed this from a very good paper, Digital Twins, from the Hartman and Hegman van der Gouweraak. I can only advise you to read it if you want to have a bit more philosophical thinking about digital twins. So if you are in the situation in the lower left corner where you have very little data, limited physical knowledge about the system, then you need to learn more. It doesn't make sense to think about the digital twin in that situation because there is just not enough backbone to do that. Then you can have situations where you can have very little data, but where the physics are very well described. Then you come into a simulation quadrant. In that situation, you can do calculations, you can predict what happens, but there is not sufficient data to calibrate or to verify or to make useful information. You could also have the other situation where you have a lot of data, very limited physical insight, and then you come into the data-driven models. At the time, it was mainly machine learning. Nowadays, AI might be taking a place in this quadrant. And you already see it here. A digital twin is only relevant in situations where you have both available, where you have a good description of the physics of the system combined with sufficient data to learn from the differences. I'll go into that later. Here you see a bit the two approaches. So to go to a digital twin, I advise you to think where in the quadrant you are. If you are in the bottom right, you have a lot of data, but not enough physical insight. You need to work on your domain knowledge. If you have a good physical model, so good insight in the process, but not sufficient data, you need to work on data capturing and on data accessibility. And we see both routes happening. So if we look at research projects, typically there is a physical model behind it, but you need to work on data side. If you look at industry processes, there's typically a lot of data, but you need to work on describing the processes, making the connections between the data, and make a model. So in essence, making a model means making a mathematical description of the process. What is both routes give the same results. There are pros and cons. So if you work with physical models as a start, you have limited data, but you have deep domain expertise. If you start from a data-driven site, there is a lot of data available, but little domain knowledge. So if you assess your situation in which you want to make a digital twin, you can derive what you have to work on by thinking on it like this. And then an important point I would also like to highlight in this introduction is that in our view on making a digital twin is that you model what you know. So if you know the physics, you make a model for it. Don't try to correlate data for which you know already the interaction. But then if you have a model of everything you know, try to correlate the differences. And I have a very nice example here. So, okay, this is just 3 chaotic lines on the curve, but there was a very interesting project behind this. So in this project, we did an assessment of estimating the melt composition. So you start from a feed mix, you have a mixture of different material streams that you melt together. From the feed mix, you can calculate the expected composition. We used a few months of data training in this to make this model a bit better. And then after this training period, we could rather well predict the melt composition. Of course, it's not 100% perfect. You have some deviations. But by looking at the differences between the expectation and the measurement, so you bring together the model and the numbers, we could detect even which suppliers were off spec. So normally you cannot do that because you have a feed mix, you have multiple material suppliers, they go in one pile and molten all together. But by analyzing the differences between expectations and reality, we could decide like, okay, this supplier delivered off-spec material on that day and so on. So that was actually a very interesting project. But enough with the philosophical. I think we can move on to the case studies, which we will present today. So we have 3 projects that will present their digital twin and how it's used in their project.
Thank you, Els. Very interesting. I also learned a lot here. So I think it should be Manuel Leuchtenmüller now.
Oh, hello, I hope you can hear me. Thank you. So I'm happy to give a short introduction into our Dust2Value project, pioneering steelmaking waste recycling, which started 2 years ago. We give a short introduction about the overall topic. We are working on this project. it's all about recycling and resource recovery. So we have scrap, the steel industry. We have electric arc furnaces. They produce again steel, galvanized steel, and in this electric arc furnace, an residue or secondary raw material is produced. It's called electric arc furnace dust, and it contains up to around 40% zinc. And this dust is currently treated mainly in the Wels process, where a secondary zinc concentrate is produced that goes to zinc smelters, so where again zinc is produced. And this process has some advantages, some disadvantages. For instance, also a Wels slag, around 650 kilograms per ton of dust. It goes mainly to landfills, sometimes to construction. So what is this Wels process? We have everyone the same level of information. It's in the end a pyrometallurgical treatment where this electric arc furnace dust is mixed with carbon on the one side, fed into a rotary kiln up to around 60 meters long. And in countercurrent direction, there is air flowing through this furnace. And the air, the oxygen reacts with the carbon, heat is generated. And in the bulk, you have reducing conditions. And the main reaction, most important reaction there is defuming, the reduction, volatilization of zinc oxide to gaseous zinc. This gaseous zinc, this zinc metal vapor, oxidizes in the atmosphere again, back then to zinc oxide, to very fine dispersed particles, and the zinc oxide is then recovered in backhouse filters. So in the end, very simplified speaking, it's a kind of a distillation process. The other side, we have the Wels slag. So some general points about this process. It's quite an efficient process because it's a counter-current reactor. So you have quite a good heat recovery. You preheat the cold material with the hot gas, and on the other side, on the discharge side, you preheat the air with the hot Wels slag. You have heat recovery of the reaction. This zinc fuming reaction is extremely endothermic. So having the reoxidation quite close to the reduction zone is important because you can recover this heat within the furnace. But there are drawbacks, and that's why we work on this project. And one of the major problems and challenges is the use of fossil carbon. The carbon footprint of this process is quite high, especially in terms of recovered zinc. As mentioned, there's also Wels slag, around 600 to 700 kilograms, with some zinc inside also. The iron is not recovered. And we estimate that around 30,000 tons of zinc end up in landfills every year in Europe alone due to the underutilization of this Wels slag. So what do we want to make different, and what is the innovation behind our project? Simply speaking, our philosophy was from the beginning over the last year to keep the strength of the Wels process, so keep this countercurrent reactor in place, replace the carbon with hydrogen in this case. And we use the hydrogen also to heat the process, not by burning it, but by preheating it and using its heat capacity. So the zinc fuming reaction remains similar, not with carbon, but with hydrogen. And what we have is a design that during the cooling, the zinc reoxidizes not with oxygen, but with water vapor. And the zinc oxide is formed again, and we recover the hydrogen, not only the heat, but also the hydrogen. And what we want to test as well is to not produce a slag material, but a kind of secondary grade DRI that can then go back to the electric arc furnaces. So as mentioned, we keep the strength, but we even improve the efficiency because we recover the reduction agent as well for the zinc fuming. heat still remains in our furnace. We replace the fossil carbon with hydrogen, so there are no direct greenhouse gas emissions. Instead of a well slag, we aim to produce a secondary grade DRI. And when we bring this DRI back into the electric arc furnace, all the zinc stays in the cycle and we have no losses of zinc due to landfilling. What does it mean in terms of process output streams? If you look at the state-of-the-art Wells process, you see that there is, compared to the overall mass flow, material flow, a relative small fraction of actual product of crude zinc oxide. And with the transition, that's our Dust2Value process, we estimate that we can have more zinc oxide because of the improved recovery, also produce this secondary grade DRI and have minor fraction of slag building compounds that go back into the electric arc furnace. In terms of reduction, kinetics, efficiency, we ran many tests over the past years, and what we see overall is that when running the tests in simulated conditions that reflect an actual scale conditions, we see that the hydrogen-based reduction has advantages because of kinetics. On the left side, we see much better zinc oxide recovery. The right side, we see also in same conditions, much better metallization. In terms of energy consumption, we see on the left side that the iron oxide reduction, the material heating, is actually a very small part compared to the zinc oxide reduction. That's what I meant before. Therefore, designing any process recovering zinc from a waste material must consider somehow to recover this heat from the reoxidation. And we estimate around 780 kilowatt hours per ton of material treated in our process, including already heat losses. In terms of consumption of hydrogen, a typical composition, when we go to iron, would mean that we need around 27 kilograms of hydrogen per ton of dust. Due to the recovery of the hydrogen from the zinc oxide reduction, we lower this to around 19 kilograms. And in, let's say, the where hydrogen is not available to a large extent, we can run the process with just partial reduction to wüstheit. So we lower the specific hydrogen consumption to only 6.3 kilograms per ton of dust treated. And in terms of emissions, when we look at the zinc production, we see that the refining and melting have contributed to around 1,700 kilograms of CO2 emissions per ton. Overall, it's around 2,600. When using pure Wells oxide, so the secondary material as a feed, these emissions, specific emissions, if you calculate it in terms of produced metal zinc, increase because of the large carbon footprint of the Wells process. With the Dust2Value technology, as already mentioned, we have no direct greenhouse gas emissions, so we may lower the greenhouse gas emissions from this resource recovery. Who is behind this project? It's coordinated by the Montan Universität Leoben in Austria. Nowadays we call us already Technical University Leoben. Together with InsPyro, MAL and Befesa, and also the Politecnico Milano, Georgs Marienhütte, who formed this consortium. We made great progress over the past 2 years. You see on the right side the CRT model of our rotary kiln, and we just had 1 week ago a meeting in Austria at Semmering at Hönigsberg, place of Email, where we visited the construction and checked the current status. We see on the top picture our preheating chamber, and we see the frame, and we see that assembling already started. So we are confident that we'll start decommissioning in summer, late summer, and first results by the end of the year. So it's a short introduction to our process, and Els, I think
Yes.
we give the word to you.
Thank you, Manuel. So indeed, last week it was a lot of fun seeing that the pilot plant is getting started, also for us as a team that models the plant, who, well, that's just computer work. It's also nice to see that in real life things are happening, and that what we do is actually supporting the works and the process development. So in this Dust2Value project, InsPyro is supporting the research by making a digital twin or a process model of the new hydrogen reduction kiln. So as I said earlier, that in a research project, it's very typical that you start from the knowledge side and that you start making a model based on the physics. And then the challenge is that you complement this model with data that becomes available throughout the project. I try to make here or sketch here a bit of a timeline for the digital twin. So we started indeed 2 years ago for the digital twin work package. That means that you start by collecting data available in literature, you start investigating the thermodynamics and use that state-of-the-art knowledge available to build a first model, and this model will then be elaborated over time. At a point in the project is that you have to transform the models built into a digital twin. That's a bit a crucial phase in this work package. And then once you have, well, in this project, once we have the digital twin in place, which will first be a standalone calculation engine, in the next phase, it will also be connected to the pilot plant. And then it really becomes interesting where you can put the measured data next to the calculated data, and then you can start using the digital twin to its largest value. So we started with building the model. What does it mean? In this case, we started out by understanding the thermodynamics behind the process. And here, for hydrogen reduction, this is very well described. So as an example here, you see a very important graph for the process. This is a mapping of the process conditions in which you can reduce the zinc oxide and iron oxide that are present in this AIF dust. So on the horizontal axis, you find the atmosphere. Sorry? Okay, that was a lapse. So on the horizontal axis, you have the hydrogen atmosphere. So on the far left, you have a pure hydrogen atmosphere. On the far right, you have a steam atmosphere, so only water. And on the vertical axis, you find the temperature. So this maps the possible conditions inside the kiln. And when you are at a certain position, at, for example, the lower right in this graph, nothing will happen. The iron will remain oxide, the zinc will remain oxide, and no reaction will happen. When you increase the temperature in a specific atmosphere, you will start reducing the iron to FeO or to iron metallic. And this orange line here is a bit the transition from zinc oxide to zinc metallic vapor. So that's a bit the threshold of the physical boundaries of the process. So this is actually very well described. And when something is well described, it's easy to make mathematical formulas out of it and to do calculations. The difficulty in this project is the aspect that it happens in a countercurrent kiln. Why is it so difficult? Because every position in this kiln has different conditions, and different conditions means that you can have reactions or not, and by having the reactions you will change the temperature, and then everything will have to balance out again. So that is the difficult thing here. I'll show you here how we do this. So we have a mass and energy calculation tool. We use MedSim as a mass and energy calculation, and it looks like this. So it's rather simple view. So on the left, you have the feed mix calculation where you calculate what's going into the kiln and in what conditions you have here. On the right, you have the hydrogen injection station. As Manuel said, this is also the heat input. So also on this side, we have the heat calculations and the possibility to control the process. But then inside the kiln, so this looks here as one unit operation, but in the model, this is actually split in 8 sections, and each section is iteratively calculated on its own to get a good approximation of what we think is going to happen in the process itself. So here, well, you see here these 8 sections. This results in a furnace profile. So for every scenario, we can calculate the expected temperature profile in the kiln. We can calculate the expected atmosphere, the expected composition of the solid. And by combining this calculation with the thermodynamics I showed on the previous slide, we can actually investigate how we could optimize the process if there are problems with temperature or reaction rate and so on. Another difficulty in this project was the kinetics. Some of you know this very well. So you have the thermodynamics, which give you the expected equilibrium of a system. But if you look at the real process, this equilibrium might not have been reached because you have kinetic constraints. These chemical reactions do not happen instantaneously. Sometimes you need to wait. Also, these kinetic constraints are included in this model to have a realistic view on the kiln process. So then we combine everything together, and then we can go back to our thermodynamics and plot on this diagram what the expected route of the material is. And from this, we can start reasoning together with the engineering how we need to tune the process so that everything, well, all puzzle pieces fall together. We make this digital twin, or this at this point in time, it's still just a model. It's not us who can do all of this. It's a cooperation with all the partners because we need to include all knowledge that is being built up during the development also in this models, so that in the end your model is also a collection of the available knowledge within the consortium. So you really need to work together with all the partners to get everything coherent inside the model. I'm still talking about the model. That's not yet a digital twin. The model is the calculation engine behind the digital twin. So in 2025, we started preparing the model to be transferred into a digital twin. So what can go wrong, or what can go wrong? That's very negative. So what are the points of attention there to make that work? Well, I've put it here in second position, but actually it's the most important. The model needs to be robust. The model needs to run for all potential inputs it can get. So that is an exercise that needs to be done to validate your model and check and double check and rerun scenarios to see if all situations lead to a converged calculation. A second point of attention is to do the data mapping. Data mapping means that you are going to decide what the inputs are going to be, the hard inputs, what are the controlled variables, and what is the calculated output. It's very important to map that out so that everyone in the consortium has the same expectations. And for us, it's also important to know what other partners expect from the model to receive. So we need to spend a serious amount of time to get into this data mapping. And once that is done, you come to the fun part. You can define the user interface, how it looks, the fancy buttons, and how you want to make the graphs and so on. So I try to sketch that here on the right, how this digital twin then has to work. So you have a user interface, which takes the input from the person who wants to do a calculation. That user input is then going into a database. And it's the database that actually triggers the calculation, that sends information to the model and receives information back from the output of the model. And then the output user interface only communicates with the database. So there is a bit of looping, but that all has to do with the robustness. The database in between allows you also to do some data validation and to do some data checking before you actually send it to the model, because this part needs to be able to run with the information it gets. So that's the scheme of the process. Then I have a bit of a scoop, because this is the first time I'm actually going to show the real interface of the digital twin. It was just finished. So when the consortium partners log into the Dust2Value, this is what they will see. They will get a dashboard where they have the possibility to start a new simulation or view their previous scenarios. So at this moment, the digital twin is a standalone system, meaning that all input comes from the user and it generates output. So the user, upon logging in, gets a screen to put in all the parameters they want to include, and then these will be used to calculate. In this first phase, there will also be an iteration between us as the making of the digital twin and the users to fine-tune what needs to be an input, what is a fixed value, what needs to be in the output, how does the report needs to look. So that needs to be fine-tuned. And then next year, we will expand this standalone digital twin to have a connection with the pilot plant. And as you saw on the pictures, we also need to wait till the pilot plant is there and generating data. So we expect that to be happening this year. And the points of attention there is that we need to expand the looped system. So before we only had the user interface generating input to the database, but on top of that, there will be also the sensors of the pilot plant that track what's going on, and we need to have those numbers also in our database. Then a combination of these two go to the model. The model calculates, returns results to the database and generates output. And once that whole system is in place and functional, and you run this for some time, you can start thinking about feedback learning mechanisms. So you look at differences between the model and the pilot plant and start learning from that. And this is the challenge that is in the last year of the project, to really close this feedback loop. And then I hope that in a year from now, we can present this whole cycle going on. So this gives you some insight in the work package on digital twin within this project. So thank you for your attention, and I think questions will be at the end in the Q&A.
Nice, thank you, Els. So now BioFibreLoop will be presented. Thomas Fischer, I think it's your turn to share your screen.
Just a second, sharing the right one. All right, good morning from Denkendorf. Denkendorf is the Textile Research Institute close to Stuttgart. And we are coordinator and partner in a European project called BioFibreLoop. We are now changing the domain a little bit. We are now going to textiles, textiles plus some technology. And that's also the interesting part. If you combine two different technology sectors, then the digital twin becomes really important because there's a lot of physics involved, unknown physics, and that's kind of interesting. But let me first, before Francisco goes into the detail of the digital twin, explain to you a little bit what our project is all about.
Your screen is not shared yet, Thomas.
Oh, sorry.
No. I thought you first wanted to say a few words.
Yes,
but
sorry for that one.
Yeah, perfect now.
Okay, sorry. I one click too
worries.
low. You missed only the introduction slide so far. Yes, we are also a European-funded research project under the European Health and Digital Executive Agency, the IDEA. We are in innovation action for 3.5 years, and we have 13 partners in 9 countries, so it's a really widespread project. And also here the digital twin is one mean of communication where all the partners can have a look and contribute, and that's really important also for our project, this aspect. We are dealing with circular bio-based technical textiles. So we have bio-based materials that we put into the textile supply chain, and we have a really cool and new innovative biomimetic-inspired non-toxic functionalization. And I will show you in a minute what this means. Basically, we have 6 pillars in our project. We have the bio-based materials. We have this biomimetic functionalization of textiles. And then we have the digital tools that pretty much cover these 2 process aspects. Then we have the industrial applications, the upscaling of this lab process we are working on. And in addition, we have to deal with recycling. We have to close the loop. Also here, the digital twin can help a little bit. And in addition, we have the sustainability assessment, product carbon footprint, etc., social analysis to make sure that our new processes are more sustainable than the old ones. Looking at the bio-based materials, we are basically using PLA and cellulose-based fiber, but the really cool new one is the lignin fibers. Lignin is a waste stream from the wood industry. It's this, a little bit like honey. It has a certain color, as you can see. It has a little bit of a smell also. It's not really something you would apply for textiles, but it's a very nice raw material, and we apply it to textiles. We do some special spinning, and of course you have to mix it with some bio-based compounds, but then you get really textiles, as you can see on the right side, a woven fabric out of it. So that's the first part and the first interesting process. In addition, we use PLA and cellulose, as I told you. Here we don't start with the spinning, but we use material and then we go into the process. And we have different processes. That's also a challenge for the digital twin. So we have non-woven materials, we have knitted materials, we have woven materials. So we have the variety of textile production processes here in our project. Here you can see some pictures of the process that will also be part of the digital twin later on. This is the second part. Now we have the textile made from these 3 different materials. And the second part is now we want to have functionalization. We want to have, for example, water repellency used for outdoor, for workwear, for all the other things. And this is, as you probably know, mostly done with PFAS and with highly hazardous chemicals. And we are looking for more environmentally friendly alternatives. And our approach is to use a lignin-based coating. So we use also the lignin, a different type of lignin, but lignin for coating process. So we add a layer of this material to the textile. And this is a process that also has not been done before in industrial environment. So we really have to do some bit of process development. There's the combination of the textile and this liquid. It's with a steel roller. It's a roll-to-roll process in the end. And it's a process that you need to be able to upscale in the end to this textile width of 2 meters or 1.5 meters to have real textiles. So this is process development, and this is interesting. And this is something you will also see later in the digital twin. And now comes the interesting part, the biomimetic functionalization, because the lignin coating itself is not water repellent, or not as good as not as water repellent as the PFAS. But now we add a trick. Now we emboss a mechanical structure like a stamp in this lignin coating, and this structure you can see here on the right side. This is just a schematic print of the structure. This structure is inspired by nature, because nature also creates hydrophobicity or oil repellents by mechanical structures. You know that maybe from lotus effects and other well-known words. So you have certain mechanical structures that prevent the water from coming in due to the contact angle of the water and the water droplets and the size of the water droplets. And this is something interesting that can prevent the water from coming into the structure. And this is a biomimetic surface morphology that we take from nature. We are inspired from nature, and we emboss or imprint this in this lignin coating layer. And we do this with these metal rolls you have just seen before. And these metal rolls are laser engraved. And this laser engrave pattern is inspired from the nature. And then we have the laser engraving pattern in the metal roll. And so we can imprint it for ongoing, as long as the metal stays in form. And this is the interesting part, and this is new, and this is where the different material sciences and process sciences and the laser physics come into play. And this is the melting point for our digital twin, that we really have a nice model to play with. And as you can see, as you can imagine, it's a lot of experiments you could do, and they are costly, they are time consuming, they are material consuming. So this is the ideal battleground for a digital twin, where we can do simulations and experiments with the twin. Here you can see a little bit the structure. One is from the filefish inspired. So these are these needles, and then you need, of course, to have the negative form of that one in the embossing process, so that in the very end, our textiles, you can see it here on the right side, on the lower right side here, have the same structure again. So you need a negative form to emboss on the coating, and then the hot or the semi-liquid lignin coating will go into these holes. So we basically are inspired by nature. Here you see another one, the rose petal. Then we take a microscopic pattern, do the laser engraving of the metal roll, and with that we go on the coating layer, and then the coating layer gets again the negative form, so that we in the end come up with this original structure from nature, put it onto our fabric layer. Yes, the digital tools for that one will be shown in a minute. Let me just briefly say some more words to the recycling. Recycling is tricky, but we have the positive aspect that we don't need the PFAS anymore, that we have more or less lignin and other biodegradable materials as monomaterials. So that's kind of the good sign. Still, we are exploring different types of recycling, thermoplastic processing or solvent extraction. So you need for all the materials the right technology and approach for the best recycling. We do this with our partner in lab scale and then also do the upgrading. Currently, our digital twin is not covering the recycling, but this might be an option for the future. And then the sustainability assessment. As you all know, the European Commission asks for full sustainability frameworks. We started on the right side from the sustainability development goals. We had different approaches, material flow analysis, traditional LCA, techno-economic assessment. And then we really do tests now in the laboratories, in the factories. We collect the air and measure the particle emissions and everything to make sure that we have a safe environmental and social production of these new textile processes. This is our conceptual framework for sustainability development. But I guess in similar projects, you also have to do these jobs. But the nice thing, also for the life cycle assessment, you need a process model. So in the end, it's all about process model. We started with one process model and we used that for the digital twin. We used that for the life cycle assessment and for different aspects. So my takeaway message really start with a process model, create a really good process model, involve all the people, and that's the basis for all the future work. Yes, you can learn more on our website, of course. We have newsletter, we have Instagram, we have all that information about our project. We are currently in the middle of the 42-month, and we are really looking forward now to go from lab scale to the industrial scale, and to really have the right settings and the right process parameters, thanks to the digital twin, which was developed, of course, by the team, but the work package was led by, or is led by IDENER, and Francisco will now take over. Thank you for listening.
Thomas, I will now share my screen again to do the presentation for the digital twin. Second. Okay. So here we are, Francisco again from IDENER, and I will now present the concept of the digital twin in BioFibreLoop. So I will start right over by explaining what the digital concept is in this project, what is the objective that it has, as described in its corresponding work package and task, is to develop and integrate digital tools for the key processes in BioFibreLoop to enable the fast and effective development of the final BioFibreLoop products. So there are 4 phases of the development of the digital twin. We are most of them on the middle of it. We started by understanding the process and collecting the key process parameters and create a first database that we could use to start with the digital twin development. So as a second step, what we did and we are still doing is to construct all the models, the physical and mathematical models for the process by integrating all the data from the materials, the operational parameters, experimental data. Also start building the visualization and the user part of the digital twin. Next, we will move on in the future. We are just starting to do it to use data-driven models that will be applied to the digital twin by using machine learning to identify and optimize the key or the optimal operating conditions of each of the processes. And finally, we will achieve the virtual tool, the global virtual tool that will simulate all the key BioFibreLoop processes and will support its industrial replication, so on in the project. So, what are the concepts of the BioFibreLoop digital twin? There are three main parts. The first one is external to the digital twin. It's the physical space, which represents the real world environment. It includes all the real units that are being part of the process, and from them we can gather the data from the experiments that are performed in the units. By analysis of the material properties resulting of it, by obtaining the process parameters from sensors, all of that will go to the intermediate between the physical and the virtual space, which is the information processing layer. It is the layer that collects and most important structures all the data that comes from the physical space, and basically builds all the models. The mathematical models are built there in the information processing layer. Is the core of the digital twin, almost like at the backend. And in the future, it will perform also a future selection by using data-driven models. And finally, we have the virtual space, is the digital representation of the physical space, and integrates everything, all the workflows, all the equipment models, and it allows for simulation to obtain predictions, do testing, and finally have results. So it also provides an interactive environment that the user can use to do the testing and do the simulations of the process, explore scenarios, and visualize the results. So how did we start? First, we needed to identify all the operational basics parameters. We did it by using three phases. The first one was about trying to model the process workflows. With this, I mean the interaction between one unit and another, how the inputs goes to the next unit and how the outputs go to another one. All the global scheme of it was designed for all the processes in BioFibreLoop. And then for all of these processes, we identified and categorized all the parameters that are really relevant to each of them. And finally, in the phase 3, the verification of all of these parameters that we identified, that you will verify with the laboratory experts and the industrial experts that are part of BioFibreLoop. So with this, you can finally have some information sheets that can include information of each of the process. For example, an extruding process in BioFibreLoop, then you have its purpose, its description, and most important, its parameters that are relevant to it. For example, temperature with their ranges, their units, comments on that. Also, we needed to gather is something. The information of the critical processes is something that we will be doing along the all digital twin development, and not something that you do just once. But for example, you have the key here data we needed, which was the contact angle resulting from different experiments. You will have a set of data that contains the name of the coating you are using, temperature, pressure, and different other conditions that will lead to a final measurement of contact angle that can tell you how hydrophobic, how oleophobic can be that specific coating in that specific parameter values. Okay, and that's something that we are trying to replicate in the digital twin to have close values to it by implementing mathematical and physical models. So now talking about the digital twin itself, it follows a current architecture of 4 folders or parts. First one is the configuration. It contains all the parameters that are relevant to the digital twin. They can be global, that affects all the processes. They can be material specific and also operational settings that we are using. Next, you have the modules, which are basically the simulation scripts that you use in the digital twin for the simulations. At the moment, the most critical part is the embossing and the contact angle predictor of the process. So that's what we have in the modules, and all of this information will go into the notebooks, which are at the moment Jupyter notebooks, which is what the users can use to run simulations, to have predictions, and to see visualization of the results. And last, utils category is basically all the rest of the Python functions that you need to use to help the other 3. Okay, the loader functions, fitting functions, and so on. And that just helper of the rest. So how are we modeling, in this case, the embossing process? So first, what we did was to collect embossing models from the scientific literature to have an idea of how it is interpreted from a mathematical and physics point of view. So after several months of literature review, we obtained the key formulas that we are using that are embedded in the digital twin. For example, here, how we obtain the height replicated from the embossing tool. First, the time of filling a cavity with a certain width and height, and how it is translated into a continuous roll-to-roll hot embossing process until we get the final equation that is implemented in the, well, all of them are implemented, but the final equation is what will give you the prediction of the height replicated in the polymer. Also, for contact angle prediction, this continues because the height that is predicted by the tool affects the final contact angle that we obtain for the polymer, for the embossing part of it. So we are using the classical Casey-Baxter and Wenzel equations that accounts for these measurements of contact angles. Finally, you can have a decision with it is more Casey state or more Wenzel state, the final result. Finally, you can have a prediction of all of these parameters, how affects the final contact angle, and try to keep up with the experimental results that the other teams are obtaining in this case for the embossing. So now I will explain how the digital twin really works from a user's perspective. First, you need to configure the files, which are in the format YML for the materials that you are going to simulate. Then you have the option also to do a viscosity fitting of the curves that are relevant to the material you want to simulate. And with these initial files, you can start running the digital twin. The digital twin, what it does is first set up the project, which is the paths, basically the Python paths that you will use for the folders and so on. Next, you load all the configuration of files. This is done just by clicking at the moment in a Jupyter notebook. And next, you have the execution of the simulations. Before that, we have also an interactive inputs editor, as you can see above, where you can change the values that you want to simulate without needing to go to the original files that you had in the digital twin. So the user didn't have to change that in the original files. And finally, you can obtain results and visualize them in different ways. You can compare experimental values with simulated values. You can also do parameter sweeps. For example, you want to vary the pressure, for example, and see how it affects the height replicated and the final contact angle predictions. You can change also the parameter geometry. You can also change diameter, pitch, depth, so on. All of that affects the final result. So what will we do from now on in the BioFibreLoop project? So what we need to do is to include all the optimization part, which will be AI assisted or data-driven assisted, that will use this experimental data set and the results from the original digital twin to identify the optimal process parameters. Next, we can start with the real validation and do the final predictive simulations of the digital twin. And finally, we will build the virtual replication tool that will be used for the textile industry in general, for the stakeholders that want to simulate the BioFibreLoop processes. All of this will result in something like this, as I'm showing you. This is for another project, but as shown in the previous also part of the webinar, this is the final user interface. Something like that should be the one that we will have for BioFibreLoop, where you can change parameters, you can see the process, and you can see the results and perform optimizations of it. So yeah, that's the main concept of the BioFibreLoop digital twin. That's everything from my side. Thank you very much. And I will now leave the floor for the next presenter. Thank you.
So I hope everyone can see it in full presenter mode.
Yes.
Okay, perfect. So my name is Schmidberger. I'm from the University of Stuttgart, and we are coordinating the EU-funded project FlashPhos, which started in 2021 and it's ending very soon in end of April 2026. So the objectives of FlashPhos are recover the usable components and ingredients of sewage sludge, recover the phosphorus in form of white phosphorus, produce a climate-friendly cement substitute, an iron alloy, and to concentrate the heavy metals in a dedicated stream. And the goal is to do that in an economical, ecological, and circular way to make products out of problematic wastes. So why did we choose to go with white phosphorus? White phosphorus is used, is the keystone for the chemical industry. You can produce thermal phosphoric acid, which is a very pure product, and you can produce any kind of phosphorus chlorides or sulfates or other phosphorus derivatives, which are widely used in various sectors. For instance, in the food industry, in the electronic industry, to produce microchips, the e-mobility, in the batteries, white phosphorus is used in some form, and one of the most known parts is as a flame retardant in the fire protection section. So what are the expected results from FlashPhos? We are setting up, and 2 parts of the 3 process steps were already operated with a total feed of 250 kilogram of sewer sludge throughput. We we want to design or make a basic engineering of an industrial plant, including a safety assessment, and to provide a solution for sustainable resource management in a full circular economy model. So coming to the FlashPhos concept and its circularity, I will go through this graph with you. As an input, you have, for once, the dewatered sewage sludge coming from the wastewater treatment plant and industrial residues, as well as process heat, which is required for certain, and electricity, which is used for certain process steps. In the dryer grinder, they are in a combined step. The sewage sludge will be dried and simultaneously grinded to a particle size where it can be used in a flash reactor, which is basically an entrained flow reactor. So the aim is to produce a very fine and dry particle in the dryer grinder. Then continued with the flash reactor, which is the entrained flow reactor. This is operated at very high temperatures to produce a slag, a gaseous fuel when operating it at substoichiometric conditions, and a heavy metal concentrate. And the last step is a refiner step, is basically an electric arc furnace for our project. And there is produced, or the phosphorus is reduced using coke, which means you produce a very high calorific gaseous fuel. You will end up getting the phosphorus into the gas phase, meanwhile producing a cement substitute as well as an iron alloy. And those 2 process steps are a very high temperature process, so you will end up producing a lot of process heat. The products, especially the ones with phosphorus, which is our main element we want to recycle, goes back through the consumers, or goes through industrial follow-up processes through the consumers into the disposal industry again, and then ending up as a resource for our process again. So as our goal in this workshop is to focus on the digital twin, I will now show you some details and some insights of the 3 process steps, so you will have a better understanding of what we are talking about when Els will show you the digital twin. So the dryer grinder was erected and operated successfully. You can see here the dryer grinder. Here you can see the grinding, the drying grinding step, the off-gas treatment, a cooling pipe to cool the dried and grinded sewage sludge powder, and in front there is the sewage sludge feed in the raw material as a raw material. Continued by the flash reactor. There we did at the beginning CFD simulations to assess the combustion behavior in substoichiometric and oxidizing conditions. The particle distribution and the interactions with the upper and the lower part of the reactor, as well as the particle agglomeration and behavior inside of the reactor for both cases. So now you've seen the models, and 2 or 3 weeks ago we had the first successful campaign of this reactor. You can see the worker measuring the temperature inside of the slag, which is stored here, and here on the right you can see the total dimensions of the flash reactor. So you have here the combustion chamber, this phase separator collecting the slag, the off-gas line transferring the slag to the post-combustion chamber. The last process step is the refiner. This one is currently under construction. You can see the core of this technology, the electric arc furnace. There we had to modify an existing electric arc furnace. This is the lower part of the vessel of the refiner, and here you can see the lid, and that's what it will look like combined when it's installed and just completely assembled. What also is worth mentioning in the context of the digital twin is our colleagues Lukas Pohl. He made a GIS map analysis, first starting identifying all sewer sludge treatment plants and clustering them to locations of high density of sewer sludge, and further down in these areas that are narrowed down with a sufficient opportunity of getting enough sewer sludge for the process. Host plants were identified where to locate a FlashPhos plant on an industrial scale, and also considering transportations from wastewater treatment plants to a host plant of the FlashPhos plant, and therefore to get to the numbers, to the required numbers, he used the digital twin as well. So we did a market study accounting the resource management and, as I mentioned before, a basic engineering of the full-scale plant. And for all of this studies, the digital twin was the basis, since it was used to upscale from the pilot plant calculations to the industrial scale. So these are a lot of project partners are involved in this project, from academia and industry. And that would be all from my side. And now Els is going to present the digital twin.
Yes, thank you for the introduction. I will dive into the background of the digital twin task in this project. So, as Christian already mentioned, this project had a rather large work package on modeling and simulation, which comprised not only the digital twin work, but also other modeling efforts that were needed to design and optimize this FlashPhos reactor. I'd like to take the same approach as I did earlier, following a bit the timeline in how we made the first steps and this project delivered a digital twin to the consortium. So I went back to the original project description, where we actually started with the conceptual process flow diagram. The main reactions of the process were mapped so that we could use to start modeling. In this project in the first year. So we started in 2021. When we started building the thermochemistry and started to grasp the behavior of the sewage sludge at higher temperature, we encountered the difficulty that this system is not very well thermodynamically described, so we had to do effort to grasp the behavior of this material. So we started off with thermodynamics to first do calculations, but actually we complemented this with several experimental results because we needed to support our model on that side. So that's what you see here. So you have here, it's a high temperature process, as Christian explained, so the material is going to be molten. So we needed to map the melting behavior of different sludges and how the composition impacts this. Then there were questions on the energy consumption related to that and with the variation over different materials. So that was actually a very difficult task to get that into a model. Then next to that, we also worked on defining operational window because, well, the goal is to get the phosphorus out of the material. So we need to find operational conditions that are reducing to get the phosphorus out, but you want to reduce the contaminants going out. So from equation perspective, the first year we had a lot of challenging mapping everything and detailing the flow diagram. But then once you start doing that, you also, well, the goal is to make a digital twin, so you need to start collecting and you need to start detailing the process flow diagram, and that's what you see here on the right graph. So you have, this is just a glimpse. The model is much larger than this, but here we have some important parts. So you have the feed preparation on the left top. This material is then going to the dryer grinder, as Christian showed on the picture, where the material is ground to a very fine size. Then this material is going to the flash furnace, where it's molten. There is a burner and the material is heated. Then you have an off-gas system, which is the fuel gas, and then you have the slag that is going to a refiner section where actually the phosphorus is getting out, and then you have a whole cooling section to get the phosphorus back out of the gas stream and a gas cleaning system. So all of that is included in the model, but that would take me more than 15 minutes to go through that. With this model, as it's already finished, I would like to draw your attention to these little entities that are here in the model. These are the controllers of the model. And actually, this is something very important when you go to a digital twin, because you want your digital twin to behave like your actual plant or to respond like your actual plant. So all these responses need to be put into equations or into rules into your model. And the way we do that is by using different type of controllers. So the goal of these controllers is to get your digital twin to respond as the real process. And there are several options depending on how the process needs to respond. So I listed here the three main types of controllers that we can use. So a first one is a flow rate controller. So a flow rate controller is a controller you put on a stream to set a flow rate. Okay, that's a very logic. The name says it itself. And this can be either an input from a user, it can be an input from a sensor, or it can be a response to another flow rate that you, how to explain it? Like, for example, a burner, if your set point is a specific fuel to oxygen ratio, then your oxygen inlet or your air inlet depends on the fuel rate that is going in. That is what the flow rate controller is doing. A second type of controller is feedback controllers. Feedback controllers are used when you want to achieve a specific set point later in the process. A good example there is when you look at fluxing strategies. If you want to achieve a specific composition at the output, you have a feedback controller that changes the input so to achieve the requested output. So it's an iterative controller. And the last type of controller that's interesting is an if-then-else loop. So that is when you want your system to react to a specific situation. So for example, the temperature in a vessel depends on multiple aspects. So you have a burner that gives energy, you have a specific feed rate, you have a specific discharge rate, the temperature from the surroundings might change, the heat losses might change. So there are a lot of parameters impacting the temperature inside the vessel. But you want to control your burner and say, well, the burner needs to work when we don't achieve 1400 degrees and it needs to be switched off when we are above 1500 degrees. That is a if-then-else strategy. It's not really, a controller is very difficult because you don't want to steer, you just want to switch it on and off, and you want it to respond to a specific situation. These type of controllers are implemented for every set point, for every response that you expect from your model. And by making them, we have to look carefully to the stability. I mentioned this earlier. These controllers need to converge to a solution. It's for a digital twin, it's different than when you do a model to answer a question. If you make a model, you run it, you see it diverges, you adapt your model and you redo the calculations. In a digital twin, that's not possible. It always needs to converge. So you need to set limits to these controllers. You need to, when they diverge, you need to correct them, and that is very important. And then these controller set points can be variables on their own. They're not fixed. So you can have your system as flexible as you want. So setting these controllers is a very important part of in the model to make it a digital twin. Then we spent more or less a year on building the knowledge base, building all the models from theoretical aspects. But then we noticed that, well, actually there are quite some gaps in the knowledge on this process. So we had a very difficult to estimate the behavior of minor elements. It was also difficult to have the kinetic constraints. This sewage sludge, it has various compositions, how to estimate the correct heat capacity to get the heat balance and so on. Is there site equipment? Because the basic concept, well, it's a very simple process flow diagram, but actually you need a lot of site equipment. Do we need to include it in the model or not? So actually the second year is to use to fill in all these gaps, to do some dedicated experiments as you see here to gain insight in the kinetics, and then bit by bit there is information collected not only by us but by the entire consortium, by doing little experiments, by gaining some insights, by doing some trials and so on. And all of this is slowly collected into the digital twin, into the model to fill in the gaps. While doing this, we need to transfer the model into a digital twin. So as in the previous project, we make a data mapping of the required ins and outs, we make a layout of the user interface, and then we started testing. So the system is the same. You have a user interface that goes to a database. The database asks for a calculation. The calculation gives results, and the output, the user interface gives the output, which it gets from the database. So how does it look? In this case, this is the interface. So you have a scenario manager on the left where you have all your calculations, you have your inputs, then you can run a simulation. At that point, what you are doing is you define your input, you send it to the database, and it requests a calculation. Then once that is done, you get an additional window here that gives the first results of the calculation. So the model gives the results to the database, and that goes to the output. And then this is a summary of the output. Then you can go a bit further by looking at the details of the calculation. So a lot of parameters can come out, a lot of results can come out of the calculations, more than listed here. And there is a comparison tool to compare different scenarios. And actually what you're doing then in the back is from your user interface, you retrieve data from the database. You're not asking for new calculations, you just look at previous results for interpretation. There was some testing by the users, so you will see the use cases afterwards, but there is some communication back and forth, like, okay, I need to do this, but it's not possible. You need to adapt the model to that, or you need to adapt the output to give me the correct information. So there is this test phase. And then the last 2 years, the digital twin has been used. It has been gradually improved. And I would like to end with a note that this digital twin is not a static entity. It's a tool that requires maintenance and updates. It needs to be alive, so to say. So every time there is a bits and pieces information coming in, it also needs to find its way into the digital twin for everyone to use. And as Christian said, we're almost at the end of the project. So it's also very nice that after this more technical explanation of the digital twin, I can give the word to the users of the digital twin so they can explain how they used it and what benefits they saw from it. So thank you for your attention.
Okay, thanks, Els, for the deep dive. I did not know. I never looked that deep into this controlling parts and so on. But what I recognized, okay, we are a bit late in time, so I'm trying to speed up, but I try to keep the funny parts as well. What I recognized is that Dust2Value, in my opinion, has the more beautiful picture for the login side of the digital twin. We should talk about this maybe later.
We're a few years later.
Yeah,
we
yeah,
also
I
learn along the way.
Okay. Coming to the use cases of the FlashPhos digital twin. So we are now in the phase where the digital twin is already implemented in the project, and we're trying to get something out of it. So what could we do? So this presentation is one side from University of Stuttgart perspective is on the material streams, and the other side is presented by Stefan Papkalla from VDZ, and this is more about the scale-up, the implementation of the FlashPhos process into, let's say, another process. Stefan will clarify everything regarding this. So what was the goal of this material stream work from University of Stuttgart in FlashPhos? So the goal was to find the optimal location for the FlashPhos process within Europe. So what did we do, or how did we start out? So we analyzed a lot of material streams, and the digital twin at that time, let's say, not coping all of the chemical elements it is coping now, already helped us a lot. But at the beginning of the project, the complexity of the waste composition was rather limited to our own waste analysis. And within the project, we created, or we added more chemical compositions, and we ourselves developed a data bank on these chemical compositions. And InsPyro always adapted the digital twin accordingly. So both database and digital twin, let's say, exchanged data on each other or grew together. So this is our login page picture, by the way, here. So what are the possibilities of using the digital twin? So FlashPhos process needs a mixture of, let's say, materials. So it has, on the one hand, the sewage sludge as the main input, and then we had to find out different additives. But searching for additives, and especially for chemical compositions of these additives, is a lot of work. So really finding out what they are made of is difficult. So the digital twin already helped us there. We could try out, we did this in a master thesis, we tried out different compositions of waste materials and could already see which influences does this have on our products from FlashPhos process. So before searching for further chemical compositions and average compositions and whatsoever, we could skip this stage by simply looking at the materials themselves in a rather raw way and look on the main influences on our process. So we could quantify this and identify the waste streams really suiting the FlashPhos process or benefiting the FlashPhos process. So Christian already mentioned, just to get you into the boat again, we are creating phosphorus, slag, an iron alloy, and a heavy metal dust that was, let's say, more specified later on in the digital twin. And this picture is, for example, flue gas desulfurization gypsum as an additive. But we could find out that we are using others. So a development path of the digital twin, let's say, together with the time in the FlashPhos project. This is the dry sludge composition that it is now. So we added a lot more chemical elements or combinations. So the complexity developed over project runtime. And what was very nice was the fast implementation by InsPyro. And it was flexible overall, and communication was very good. So we could always add users like research assistant, and we got master thesis out of it. And there was one master thesis identifying the additives that are very beneficiary for the FlashPhos process. And a second master thesis you see here that looked on the location for the FlashPhos, which was the main goal. So you see here sewage treatment plants all over Europe, and we could narrow down the, let's say, most suitable FlashPhos locations to disagglomeration areas. Later on in two slides, we're going to see a focus of this area, and Christian Schmidberger already showed you a focus here of this recovery area. So we could not only use the digital twin for finding the right additives, but we could also use the digital twin to evaluate these areas. So how did we use it precisely? You already heard that the FlashPhos process is made out of or comprises three aggregates: the dryer grinder, the flash furnace, and the refiner furnace. So all of this was implemented into the digital twin and was arranged in some times, and mass flow inputs changed. I come to this on the next slide. So we used this digital mirror to quantify the recoverable phosphorus amount within our areas. So we could evaluate these locations. And this evaluation also coped with a different fuel mixture, so with the different additives, allowed us to find out which are the most suitable spots for the FlashPhos process. And this was and has always been a continuing process of exchange as well. So I'm now coming to the, let's say, latest exchange or adaptation of this, the adaptation of the mass flow and the scale up. So Stefan Papkalla is taking over soon and showing you what the digital twin enabled us to do with scaling up the process. So with this material stream perspective, it was always about the pilot plant scale. And Stefan and VDZ, they did fuel input amounts in the digital twin that are adjusted now to rather scale up amounts, and they focused more on the energy within the process. So not on material streams alone, this was already done, but they more focused on energy and adding FlashPhos into another process. And here you see this zoomed in recovery center, or an exemplified zoomed in recovery center. And that's it from my side. And Stefan, I'm doing your slides now.
Yes, thank you, Lukas. Yeah, my name is Stefan Papkalla. I'm, as Lukas said, I'm an employee of the VDZ. The VDZ is a kind of the German cement association, and our part, or one part of us in the project, was to investigate the integration of a FlashPhos plant into a cement plant as a host plant. And the idea of that was to make different synergy effects usable. The main synergy effects we investigated were that the first was that we use in the cement process the pyrolysis gases coming from the FlashPhos plant as a fuel substitute in the clinker burning process. And the second synergy effect was to use the slags coming as a side product from the FlashPhos process as a secondary cementitious material, so that we can replace a part of our cement clinker in cement production. For our investigations, we developed first a business case scenario together with our project partners in the working group, and we set here the important boundaries for our investigations for the scale up scenario of the pilot plan for the industrial scale up, and we used the data generated by the digital twin of the FlashPhos plant as an input parameter set for our own simulation. We conducted we simulated the clinker burning process, and the outputs of the digital twin were a part of our inputs for our simulation. Yes, thank you. You skipped already the page. Here you can see the main data set we used from the digital twin. Here are two different scenarios shown. Mainly we investigated the influence of the pyrolysis gases when we use them in the clinker burning process as a fuel. And here it was very beneficial that we can play around with the digital twin, that we can generate data sets for various scenarios. Also very quick changes were possible, and also the information provided by the digital twin were available for us without being dependent on other project partners, which is sometimes a bit time intense, maybe you know. Okay, maybe we can skip to the third and last page. What we pointed out in our studies was, as I said, the influence of the integration of the fuel gases, the pyrolysis gases coming from the FlashPhos process. This was very important because we have so far no real FlashPhos plant existing, and therefore the digital twin and the information given by that was very essential for our work. And what we pointed out here was that the fuel gas quantity and quality of the pyrolysis gases coming from the FlashPhos process are the main effects when we evaluate the impact by integrating the FlashPhos process into a cement plant. So it affects our clinker burning process significantly. So we say an integration is very challenging, but with some planned adjustments of the clinker burning process, or in the clinker burning process, we would say it would be possible, but we think that this is very specific on the plant layout and also on the location of the cement plant when we talk about the a real use case when we integrate the FlashPhos process into a cement plant. This is a very short wrap up of the work we conducted. We have in the middle of April our closing event of the FlashPhos process project in Leoben. This is something which is where you can join online or in person. And if you are interested in more information or more results from the FlashPhos project, maybe you are interested in joining our closing event in April. Thank you.